Hello friends. Today's session is on image classification, machine learning techniques for land feature classification. This is part of the course on geospatial analysis using Google Earth Engine. My name is Prasun Kumar Gupta and I am with the Geoinformatics department here at the Indian Institute of Remote Sensing. So in today's session, we will talk about classification of satellite images using supervised learning and unsupervised learning methods. In supervised learning, I will be telling you about classification and regression trees, popularly called as CART algorithms, and random forest or RF algorithms. In unsupervised learning, we will talk about the k-means approach, and once we are done with these classification techniques, we will see how to do the accuracy assessment of these classification techniques. So this session is completely on coding with Google Earth Engine using the JavaScript programming language. Also, let me remind you again that we do have an in-person course here at IIRS Dehradun from 29th of April to 3rd of May on cloud computing using Google Earth Engine for spatiotemporal data analysis. And it will be an in-person course, so you can come here to IIRS and interact with the experts and do this course live. For this, you must have a postgraduate degree and should preferably have some knowledge of geospatial data and computer programming. To apply for the course, you need to go to this link given on the slide, admissions.iirs.gov.in/short course. You need to fill up a registration form, pay a small application fee, and once you're shortlisted, you can come here and attend the program. There are limited number of seats. There are only 20 seats for this program this year. So I'd suggest that if you're interested, you should apply immediately. The last date for applying for the course is 3rd of March, so about 12 days. So this is a very good experience to come to IIRS and visit the Dehradun city and attend a course on Google Earth Engine. So let's jump into what is image classification, what do we mean by image classification, what are the input requirements, and what do you need to know fundamentally before actually start coding. Okay, so basically image classification deals with labeling an image. Okay, so we will talk about different processes involved in image classification. First is training data collection, then selecting the classifier, then training the classifier, and finally getting the classified outputs. And classification is used in a broad range of subjects, not only in image processing. You could use it in signal processing, in mathematics, statistics, data mining, and so on. And classification is slightly different from regression, because in regression you try to predict a continuous variable. So a very simple example of a regression is least square regression. Okay, so you have an x, you have an y, and you try to fit a straight line between your two data points, and you get an equation, y is equal to mx plus c. So that is regression using the regression equation. Now for any unknown point, you can predict a value, a continuous value. Whereas classification deals with predicting a categorical variable. So you're talking about discrete values like class labels or some kind of hierarchical value. So this image shows very nicely what we are trying to attempt here in this tutorial. We have n-band satellite images, and for each pixel, based on the pixel value, we are trying to predict whether it belongs to class A, B, C, or D. So the input is a multi-band satellite image, and the output is a single band classified output where pixel value will is refers to the class. So for example, in class A, I could have probably given 0, class B is probably 1, class C is 2, and class D is 3. So there are, so we are talking about pixel-based classification, right? This is slightly different from image-based classification, as in using uh, uh, image slices. Here we are doing it on pixels. And primarily there are two broad categories of classification algorithms. One is supervised and the other is unsupervised. So first we will talk about the supervised classification techniques. Supervised classification uses training data set known as labels. So for example, for each pixel uh, you have n bands, so you have n values for each pixel, and then the corresponding label. So it could be a forest, it could be water, it could be agriculture, it could be built up, and so on. So the label in case of image classification is the class label. Okay, and that primarily depends on the spectral characteristics of that land cover class. So in yesterday's session, I believe Shailja must have talked about how you have used different indices like NDVI, NDWI, NDSI, snow index, water index, vegetation index to delineate which is forest, which is vegetation, which is not, which is water, which is not, which is snow, and which is not, right? So how is that happening? Because there is a definite signature in spectra of these different classes. So by exploiting those spectral signatures, you can find out what kind of land cover that class is. In this case, we are not going to create these indices, but we are going to feed these pixel values, the individual points in the spectra, to a classifier, and the classifier should learn that if the values are like this, then it is vegetation. If the values are like this, then it is water, and so on. So we have to give some training data. Now this training data is very specific to supervised classification, and these are called labels. So there are primarily 4 steps involved in doing supervised classification. One, we need to get a scene. Scene here implies a satellite image. Second, we need to collect some training data, some ground samples. The best thing to do would have been to go on the ground and take your GPS receiver with you, a GNSS receiver with you on the field, and take a notepad and note down, okay, at this location there's a forest, at this location there's a water body, at this location there are buildings, and so on. So depending on the number of classes, you collect that many number of training samples. For each class, some X number of samples. So if I have, for example, let's say 5 classes, then depending on how big your area is, you take somewhere from 10 to 100 points in each class. So if we take 100, then 5 labels, 100 in each class. So 500 total points you have to collect. So today we will do it all on Earth Engine. We will not be collecting data from the field, but we will see how to look at the image and try to guess what the value is going to be, and put points there which will act as a training data. Next, we are going to train a classifier. As I told you, we'll work with CART and RF, and then we will classify the image using the selected classifier. So first, let me open Earth Engine. So as already told to you in 3 sessions, Earth Engine is a platform made available by Google, which is currently free for academic purposes. And you need to create an account on this. So you need to go to just search Earth Engine sign up, and it will take you to a link where you have to sign up for Earth Engine. Once you tell why you want to use Earth Engine, they will grant you access. Once you have access, you go to the code editor which looks pretty much like this. There is a left hand pane which I have sort of reduced so that I have more space to show what is happening. This is the place where you write your code, and this is the map, and this is the where you get your outputs printed. Okay, so let's me first start by making a point. So pt is a variable. I create a variable called pt, which I am going to store a point, and I am going to create an object of the class ee.geometry. So this is the shortcut if you want to like ask Earth Engine to guess what you're going to write. You can let me make this full screen. Yeah, you can just type ee dot and then give control and space bar, and it will give a list of the options which come after ee dot. You can say geometry and then press tab. It will expand. There are so many geometry options. I am interested in this function, this class ee.geometry.point. I click on it, and then I have to give my coordinates. So I need coordinates for Dehradun. Now, for example, you are going to use it on some other area. Let's say, for example, let's take Pune. You want to do the same thing over Pune. You go to and click on this tab here which says inspector, and you click on Pune city, and you will get the lat long of your Pune city. You just need to type that here. Okay, so right now I am going to go to Dehradun because I have some data ready for Dehradun. Okay, and I am going to click here. It is giving me a coordinate value, so let's me just type it here, 78.0326 comma 30.3168, and let me get a Landsat image. Okay, so as I told you, or as has been told to you in previous sessions, you need to have a look at the code snippet for different image collections. So in case of Landsat 8, let me just. So when you go to this Earth Engine data catalog, there are some shortcuts for different common satellite images, Landsat, MODIS, Sentinel. When you click on Landsat, it will tell which one do you want to choose, Landsat 9 or 8 or 7 and so on. Let's take Landsat 8, and in this also, whether you want surface reflectance, top of atmosphere or raw images, we'll take the surface reflectance product. And this is the image collection we are interested in. So we just need to copy this from here and paste it on my Earth Engine interface. So I'm creating a variable called Landsat, and I'm saying that from this image collection, kindly select only the images that cross my specific point. But that itself will be a lot of images. Let me show you. When I say print Landsat, it says there are 222 images over that single point. So let me filter it further down. I'm going to say filter date. I'm saying, okay, let me get the images over 2019 -01-01 to 2020-01-01. So this is in this format, YYY, then MM, then DD. Okay, so you need to write that. And now let me print this again. It says now there are 19 elements only. But of these 19 elements, you will see that a lot of images have a lot of cloud in them. Okay, So let me just tell you. So there is this image which has about 17% cloud, and then this image has 55% cloud. So half the image is cloudy. You cannot see anything. So we need to filter it based on cloud cover. So what I'm going to do is I'm going to say sort it based on this property called cloud cover. Okay. So I'm going to say sort it based on this cloud cover, and then take the first image. Take the first image in that sorted list. So it has sorted based on the cloud cover property in ascending order, and I'm taking the first one. That means the image which has the least cloud cover in this entire 19 image collection. So now if I see the property, it says cloud cover is 2%. So in 2019, of all the 19 images it had, the image with the least cloud is the image which is captured on 28th of April. This I am telling by looking at the name of the image, uh, year, month, and day is written. So on 28th of April, uh, an image was captured which has only 2% cloud cover. Okay, so now let me try and add it to the map. So map dot add layer Landsat, but this will not help me because it is a multi-band image. Now I have to create something called visualization parameters. So let me call it var viz, some min max values. Let's say min is 7,000, max is 12,000, and palette need bands. I need some bands. So let's make a true color composite. So for that I will need red, green, and blue. The names are SR underscore B4, B3, and B2. So SR underscore B4, B3, and B2. So hopefully this should add the image. Okay, we need to stretch this a little bit further. Okay, let me refer to my documentation a bit. 432. Oh, did I not give? Oh, sorry. I created the variable, but I did not provide it to the map.add layer. So I have to say Landsat, comma, based on this visualization parameters, and let's call it Landsat image. Okay. So now I have a Landsat image over Dehradun city, and this is quite a big image. As you can see, it covers a lot of area, starting from below Haridwar and as up to as high up to some parts of Himachal, and then some parts of higher reaches of Uttarakhand where you see snow and all. Okay. So what have we done till now? We have just given a point, and for that point, for the 1 year, what is the best image available in Landsat? We have extracted and we have shown it on the map.add layer. Okay. Next and the most important thing is now creating the training data. Okay, so we have to create points. So right now for this example, we are going to take these 4 classes. Class 1 would be forest. We'll give it a code 0. Developed, basically referring to urban or built up or settlement, whatever term you want to use, by giving the code 1. Water is given code 2, and all the other types of vegetation, let's say cropland or the other shrubs or other kind of vegetation, as class code 3. Okay, so we know these 4 classes, and now we have to create these points which will act as training data. Okay, so how do we do that? We need to go to the geometry tools here in the display only. Okay, so let me first zoom in to There is a forest range right below the Dehradun city. We're going to zoom into that a bit. So you can see this dense forest here. This is the Lachiwala range, and this is also a forest patch here. So we are going to give some training points, 25 training points, or for the example, let's keep it small in favor of time. So how do we create it? So first we have to say we want to add some points. So you click on this icon here, which looks like a marker, a balloon sign, and then it creates a layer called geometry. By default, the name is geometry. So we are going to change that. We are going to click on this gear icon which says edit layer properties, and we are going to call it forest. Okay. And very important thing is, now since we want to give a code to each of the layers, we need to make sure that this is not geometry, this is a feature collection. Why are we giving this a feature collection? Because it allows me to add a property. I'm going to add an attribute. So if you know GIS, so we are basically doing, what we are doing is we are creating our columns, our fields. So I want to create a field called class, and I'm going to give the value for forest, the class code is 0. So I'm going to say 0 here. Okay. And I'm going to give a color to it too. So it could be a green color, something like this, or there are some specific color codes given here. You could use those. Okay. Now next, just click on the place where you want to say this is a forest. You just click here, it creates an icon. You click here, you click here. Just make sure the points are well spread out and they are not clobbed up in one single place. Okay, these are all forests in and around Dehradun city. So I have just created 9 and one more, let me put somewhere here, 10. Okay, so I have created 10 points. Now you click on exit and you will see that your 10 markers for forest has been created. You could have, I could have also given it on higher reaches, anywhere in this satellite image. Just for, I'm just showing you the technique how it is done. You have to click on plus and then add these markers. One very important thing is sometimes we need to maybe continue our editing later or add and remove points. So how to edit them? You just go and click on this layer again. So editing is on. Now if you want to select an existing point, you click on the hand icon. Okay, and then you click on the point. So let's say I want these points are a bit close, so I just select one point and then press delete on the, or there is a delete button here, so that helps me delete it. Or if I want to add another point, I could, yeah, let me take a bit of dark green pixel. So like this you can edit the points later also. To zoom to all the data points you have created, there is this new record which is created. You click on this GPS icon like button, center map to record, and you will see that all the 10 points are now visible and centered on the map. Let's create one more. What is the next class? The next class is developed, which is basically built up area. So all this is Dehradun city. Dehradun city interestingly has a lot of vegetation within the city. So you have to be careful where you place the points. So for this, I'm going to take the help of the satellite image, Google satellite image also. But again, remember that your training samples should be based on the Landsat image and not the Google image. So just for reference, I'm keeping it, but make sure that you put the points on the Landsat image. So we click on add marker and it brings the same option, forest. Now we want a new layer. We don't want to create forest points. We want to create developed points. So we click on new layer. It creates another layer called geometry. We click on the gear icon and then rename this to developed make it as a feature collection, add a property called class, give it the value 1, which refers to developed. So let's say I'm going to give it red. I click on OK, and then I'm going to place these points on my built up area. So I have created these 10 points. Okay, now I have 10 points which are referring to my developed. Okay, so now I have two feature collection. One is for forest, one is for developed. The next one is, I think, for water. Yeah, water with class value 2. So I'm going to say add a new layer. I'm going to edit that layer. I'm going to say this is water layer with feature collection class value as 2. And I am going to change the color to the color given in my handout, which is this value, copy, paste, which is a different shade of blue. And now I'm going to place water points. Now water points are very tricky. The first water point I'm going to place is near this place called Asan Barrage. I think this is where the barrage is. Yes, you can see water signatures. So we're going to place my points, 2 points here, 3 points here, let's say. Then there is another big water body in this image called the Ram Ganga Reservoir. Okay, so I'm going to, so you see these water signatures here. So I'm going to put some more points here. Okay, 7. I'm done with 7. There's one more near Haridwar called the Bhimgada Barrage. Yeah. So I'm going to place some points here too. Okay, so now I have 10 points for my water bodies in my study area. And finally, we need to make one more layer. This will be for herbaceous, basically referring to crops and other vegetation. So let me take this name. I'm going to say add a new layer and edit that layer, call it herbaceous. This is going to be a feature collection with class value as 3 as given in this table. Okay, and I am going to give it a different color, which is a different shade of green, brown, and click on OK. And then there are so many cropland, cropped area. You can look at the satellite image and you can see this distinct cropping signature, rectangular pieces of land. So we're just going to add that values to my okay. Now I have some 6 points here. I'm going to a different place. I'm going to say these are also my croplands. Okay, so let's finish this. Now I have 10 herbaceous points also. Okay, now that's it. Now I have my training data which is ready. So I have I have in my image, in my satellite image, I have created, although this is very less depending on how large your area is and how many variations in tone you see. So for example, quite a lot of these are forest. Okay, so also there is a Tehri reservoir. I could have taken water points here also. There is a Tehri dam. It's a very big reservoir here. This could also be water points. Okay, anyhow, the point is, uh, if you notice carefully, there is so many different signatures of water. This water here looks more muddy. This water and little different shade, whereas the water body here has a different shade. Okay, so depending on how things appear in your satellite image, you may need to take a larger number of training data sets that will improve your accuracy. Now you will see that we don't get some very great accuracies, but no, we do not get a very great classified image, but yes, this can be improved by taking more number of training data points. Okay, so this is one major step which is complete, wherein we have created our training points. Okay, now next step is to take these training points and then to uh, uh, okay, and then combine them together into one single uh, variable called training features. Okay, so I'm going to use the same code and I'm going to add this line. Training feature is equal to, I'm going to just explode this a bit. Training var training features, that means I'm going to create a variable called training features, is a feature collection which is made by combining the four uh, layers that we just created: forest, developed, water, and herbaceous. Okay, again, these are all variable names. You can take any variables name you want: forest, crop, built up, etc. Okay, and then I'm going to flatten it. So what is this going to do? Let's me print this and see what is this value. Training features. Let I think it is a spelling mistake. Yeah, so I'm going to just go to the console, and it now says training features is a feature collection of 40 elements. If you expand it, it says it is a list of 40 elements, and each list has these property class. Each element in the list has a property class. So there are 10 of class 0, 0 to 9, and then again uh, feature 1 underscore 0 to 1 underscore 9 has the class 1, and so on. So we have 3 classes and 10 points in each class. Okay. Next, what I'm going to do, I am going to select the bands on which I'm going to run the model. I don't need all the bands. So if you look at the Landsat documentation, it says there is band 1, 2, 3, 4, 5, 6, 7, and then there is a quality band, and then there's band 10, and then some other bands like atmospheric transmittance, pixel distance to cloud, so many other bands. We don't need all this. We need band 1 to 7 and the band 10. So we are going to create a subset of the image that we have selected in the beginning. So this was the image that we collected in the beginning. From this, I'm going to say I'm going to select landsat.select certain number of bands. So what are those bands? It is going to be these only: SR, B1, B2, B3, B4, B6, 7, 8, and then 10. So I think I have that written here. I'm just going to copy this and create a new variable called prediction bands. Okay. Now I'm not saying right now, okay, you take only these. I'm not saying you create a new image with these bands, but rather I'm just creating a variable called prediction bands, which is a list of these values. Why? Because I can specify to my classifier that I'm going to give an image, and the image may have many number of bands, but you use only these bands for your prediction. You don't use the rest. Okay, so that is what is going to happen later when you come to training the model. Now what we're going to do, next step is, uh, from the image Landsat, this image Landsat, select these bands. So from the whole image, I select these 7 plus 1, 8 number of bands, and from those bands only, I take samples. So if you have used GIS, what we are doing is basically raster value to point, or sampling the image values to those points. So for a given point, what is the pixel value in all these bands? In simple words, what is the pixel value on a given point for all the bands, for these 8 bands? So that is what is happening with this sample regions function. Okay. So what it says, from the collection training features, this training features feature collection, add a property called class and take the raster values from these bands and then append to it, create a sort of a vector point file. Okay, in simple, let's talk in simple GIS words. We are creating a point file. We have 40 points we created initially by digitizing. For each point, I have a value called class 0, 1, 2, 3. So there is one column. Now I'm adding 8 more columns. That is, what is the raster value? What is the value in the Landsat image for those 8 bands? Okay. So let me do this and let me print this classified training so you can understand better what is happening here. Okay. So let me expand this. It says it is collecting a feature. So feature collection has 40 elements, same as the number of points that we digitized. And for each point, initially we had only one value, one column or one attribute called class. Now we have 8 others, which are basically uh, pixel values for all the 8 bands, band 1 to band 7 and band 10. So these are the pixel values for that point. Similarly, for any given point, what were the class value was 2, which we initially gave, and what are the pixel values on all the 8 bands. That this function, sample regions, has collected and created a new feature collection. Okay. Now this feature collection will go into our classifier. Our classifier will look at these values. It says, okay, for these 8 reflectance value, I am supposed to understand this is class 2, or these 8 pixel values, the class is 0 or 1 or 3 or something like that. Okay. So that is how the classified training, supervised classification will happen. Before we go into supervised classification, there is one more step that I want to tell to you about. This is something very specific to machine learning. That, let's say I have created 10 points. I do not want to give all the 10 points to the mod for classification. I will give only 70%. Let's say 7 points for training the model, and then 3 points or 30% points for checking whether the model output is correct or not. Okay. So what I'm going to do is I am going to partition the data into training and testing sets. Okay. So let's look at this code. This is very interesting code. This is something very specific to Earth Engine. So what they're doing is, in this feature collection called classified training, they are adding a random column. So a new column is getting added, which has random numbers from 0 to 1. Okay. And this random column adds values as uniformly, which are uniformly distributed. So the probability that the value is less than 0.5 will be 50%, greater than 0.5 will be 50%. So the probability which is, so here the train test split is at 80 or 80%. So anything less than 0.8, 80% of the points will be there. So out of 10, 8 points will go into training, and anything greater than equal to 0.8 will go into testing. Okay. So That is, out of 10 points, 2 points will go into testing and 8 points will go to training. So now from this feature collection classifier training, I have split it into two different feature collections, or two different point layers to be simple. One is called training set, the other is called testing set. Now using this training set, I will do my model training. So now we come to the point where we actually select a model and train the model. Okay. So right now we are working with classification or regression trees, or CART algorithm, which is also called decision trees. It basically takes decision based on the features, in this case the different column values, the band values. So for example, if the NIR band value is less than 78, it will be labeled as water. If it is greater than 78, it will then check what is the red band value. If it is greater than a certain number, it is urban. If it is less, so it will do a if then else kind of a thing. So if a condition is met, it is this class. If it is not met, then check for another condition, and so on. So this is done based on some criteria. It could be entropy, Gini, and so on. So machine learning, you need to go into details of how these algorithms work, which we will not do now. Basically show you how it works in Earth Engine. So the line is very simple. There's only one line. It says var classifier is equal to ee.classifier.smileCart. The name of the function is smileCart. Oh, this is a good point to tell you that there are many such classification algorithms built in Earth Engine. So if you go to this docs tab and you click on this, expand this tab called classifier, you will see that these classification algorithms are built in. So you have smileCart, which is nothing but the cart classifier. Then you have the decision tree, you have the SVM or support vector machine, then you have minimum distance, then there is a smile random forest, and so on, KNN, and so on. So these are all your classification algorithms. Now, some of them have the word smile in the name. I was trying to look up why it is called smile, because there's a library they use at the back end, a Java library which kind of helps them do the classification, statistical machine intelligence and learning engine, which is shortened as smile, and they are using this code to generate your outputs. But yeah, you don't need to learn smile, how to code in smile, but yeah, that is why the word smile in the name. So these are all the classification algorithms. Later, we are going to do unsupervised classification, which is also called clustering. So they have another list of clustering algorithms, like cascade, k-means, x-means, and in their names they have a word called Veka, W-E-K-A, in the name of the algorithm. Veka again is a tool developed by a university in New Zealand, and that helps it do machine learning in Java. So yeah, they are using these algorithms to do the clustering stuff. Okay, so that is why the names Veka and Smile in the name of these classifiers. Okay, anyhow, that is just to tell you that there are many built-in classification and clustering algorithms. Let us try to implement two of them and see how it works. So this one line does the model training. The line is var classifier. Classifier is the name of the variable. The class we are referring to is e.classifier. The function we are calling is smileCart. This creates a empty classifier. Then this empty classifier, we train it. So we call the train function on which data? On this training set data. So we say features is the training set. What is the column which is the label? So label column is called class. And what is the column which is used for as your inputs, which is your dependent and which is your independent value? So the dependent value is class, and the independent values are all those values in uh, my the band names, which is the prediction bands. Okay, so if you look at this, so based on these values, SR underscore B1, B2, B3 up to B10, these are my independent values. I am trying to predict the dependent value, which is the class value, right? So, uh, so that is what we are telling it here. Once this is done, if I say print classifier, I think it will not, it just gives that it is an object. Yeah, it has some these input properties and so on. It doesn't give much, but if I say classifier dot accuracy, I think it will come later. How to print the accuracies and all. So let us assume it has trained the model. Now using this trained model, I am going to run it on all the pixels of the image and see what is the output like. Okay, so we are going to copy this code and paste it here. So what is this code saying? It says take the image, select these bands, and classify it based on this classifier that we have just created. Got it? So we take the image, we create a subset, we say take only these bands, and of that image, you classify based on this classifier which we have just trained. Okay, so it creates a classified output, and then we say map dot add layer classified. This visualization parameter is just to tell what colors it will be showing. So the forest will be shown as green, the water will be shown as blue, etc., etc. So let me run this. I'm not expecting a great output, but yeah, but you would roughly see that the water bodies have been correctly identified. The in the cart classified output, the water bodies have been correctly classified, the forests have been correctly classified, the urban areas or built up areas is more or less correctly classified, but again you would see that the dry river beds are also classified as urban area. This is a recurring problem. You need to find out ways to solve this problem by either adding more number of points or tuning your classifier and so on. So just to show something within 1 hour's time, this is a good example. Now let us try to implement the, so yeah, this document says you need to either collect more training data or tune the model or try other classifiers. So let us, or maybe add more predictors. This is something which is a lot of people do in the Earth Engine community. What they do is they add NDVI, NDWI, NDSI, all these as features in your feature collection. So not only just the band values, but uh, arithmetic outputs of these band values. So it could be an NDVI or it could be some other index based on these and also added as a new feature. Now let's do random forest. Random forest works on a tree-like structure where it creates n different outputs and then majority voting is done and then give the final result. So again, the classifier itself is just one line of code. Then the next two lines is to classify the whole image and add it to the map. So let me just copy this and paste it here. So this is the RF algorithm. So the RF algorithm itself is just one line of code. RF classifier is ee.classifier.smile random forest, and then it takes a seed value. This seed value is just to make sure that your results are reproducible. You run it once and then next time you run again you'll get a different output. To avoid that, you give a seed value. and then train it based on the training set. The dependent value is class, the independent value is the prediction bands. Then once the classifier is trained, you take the Landsat image, select the prediction bands, and classify based on this newly created RF classifier. So you get a classified output, and then you add it using the visualization parameters. And now if I run this, you will see two outputs. One is the card classified output, the other is the random forest classified output. It is very interesting to note that you can do such things so quickly in with lot of gaps. Also, I have written 65 lines of code. The same thing when you want to do it in GIS or Python, you need, or not on Earth Engine, you would have to download the data, collect the points, use GIS, and then go back to Python or some other tool to do this machine learning based classification, and then come back to GIS. So a lot of flipping between softwares, writing a lot of code, downloading a lot of data to finally come to this result, which is easily doable in 65 lines of code in Earth Engine. So you see RF is doing better in some places and doing bad in some places. So you see these water bodies were better distinguished in CART, but it was saying that these are also urban areas which are actually dry riverbeds. In the RF output, these have reduced, but also what has reduced is the water body detection. So we could also create an ensemble of these classifiers, join the two outputs, and do something new. Or we could, in the RF classifier, we have some hyperparameters. Let's have a look at these hyperparameters also. So for example, in CART algorithm, there is two hyperparameters, maximum nodes and minimum leaf population. Now you can try changing these to tune your hyperparameters to get what is the best output. By default, it tries to defaults to no limit and take some default values. Default value is 1. You can try changing this 1 to 2 or 3 or something else, and see whether it improves your output. So that is called hyperparameter tuning. So we have our two outputs, which are basically outputs from my supervised learning of the image using the geometry points that we labeled. Of course, when you do it for a given project, make sure you create adequate number of points in each class. Some classes may be very small. So for example, in an area, the water body may be very small. So you may only get some 5 points. Other classes are very large, so you get 50 points. So you should try to avoid such situations, because then it creates what is called as a class imbalance. So a class has more number of points, one class has less number of points. So you will face such problems in real, or when you're trying to do it on a real project for a different place. Okay, so this is about supervised classification. Let us now move to something called unsupervised classification. Unsupervised classification is, how is it different from supervised? It doesn't need labels. It doesn't need those geometry points. You can simply take the Landsat image and tell I want 20 classes, and it, based on the spectral properties, it will apply some different algorithms and create these 20 classes. Okay, so just to help you understand that we are doing something else, not the same, we are not using the same geometry inputs. I am going to copy part of my code and go to a new script. And this code is just taking the point, filtering the image collection down to one image, and then adding that image. That's it. There are just 1, 2, 3, 4 lines of code, and I have the image here. Now I want to do clustering or unsupervised image classification. For that, I need to add just one line, which is landsat.sample. or this image name is Landsat. So Landsat dot sample for the given geometry, that is for the given rectangle, I want to create 1000. I want to ask it to create 1000 points. Based on those 1000 points, I want it to. Oh, right now it is just taking these 1000 points, and then using these 1000 points, it is going to train a classifier, uh, k means classifier, and create 4 different classes. Okay, so once I do this, and let me just print this to help you understand what is this clusterer output. It will say it is, oh, it's just a, okay, I need to modify it a little bit further. Okay, let's use this algorithm clusterer, and I'm going to classify my Landsat image, or cluster the image. Instead of classification, I'm call it clustering. So take the image, cluster it based on this cluster which we have just created, and create this output called k classified. Add the k classified map using random colors and see the output. So what it has done is basically it has created 4 different classes, 1, 2, 3, and 4. Why 4? Because we wrote this number 4 here. If we change this to, let's say, 5 and run this, so we get 5 different classes. So 1, 2, 3, 4, and 5. You can see 2 different colors here, brown and pink. So different clusters it has created. How does unsupervised classification work? Once you get these outputs, actually you should run it for like something like 50. You should get 50 different classes and then merge these classes. So merge these classes and then say, okay, this is also forest, this is also forest, but this is urban, but these are not urban. So like that, you create larger number of clusters, and then you merge these clusters, or you could say you could recode the output, and then create your final classified image. So that is about clustering. We've just explored one clustering algorithm called k-means, and we've explored 2 supervised classification algorithms called CART and random forest. Now we come to the section on accuracy assessment. Any machine learning algorithm, or any algorithm for that matter, will give you some output. Now you need to verify whether the output is correct or not. So how do we do that? Remember, we had set out a set of points for testing our output. So we did the classification only on our training data. So out of 10 points, 8 we used for training the model. Now I still have 2 points which I'm going to use to test whether my model output is correct or not. Okay. So for any given class, we can create something like this, a confusion matrix. So if the class is positive and the actual value is positive and the predicted value is positive, it is called a true positive. If it is negative and the predicted is also negative, it is called true negative. In the other cases, it is called false positive and false negative. So these are the cases when the model is correct, when you're getting true positive and true negatives. And a summation of that will give me the overall accuracy metric. So overall accuracy basically refers to true positive plus true negative divided by the number of points. So for example, this is just an example case. Let's talk about forest. So 307 places there was a forest, and the predicted output also said it is a forest. And 661 places there was no forest, there were other classes, and the predicted output also said that there are other classes, it is not forest. In these number of cases, approximately 14 plus 18, about 32 number of cases, the reverse happened. There was a forest and they said there is no forest. The output said there is no forest. Or there was no forest initially, it was a water body, let's say, and the output says there's a forest there. So these are wrong cases. So these are the 2 right cases. So we'll add these 2 and then divide it by the total number of points. So the total number of points is 1000. If you add these four numbers, you get 1000. And the correct times is 307 plus 61, which is approximately 968. So 968 divided by 1000. The overall accuracy of this model, this sample model, is 96.8%. So same thing we can also calculate for our case. Then there are something called producer accuracy and uh, user accuracy, consumer accuracy, or also called the user accuracy is also called the consumer accuracy. So producer accuracy for forest is basically true positive divided by true positive plus false negatives, and uh, producer accuracy for non-forest classes is true negative divided by true negative plus false positive. So you can just add the numbers in that table and calculate these values. So in Earth Engine, you don't need to actually write these formula anywhere. There are direct functions to do that. To calculate your user accuracy, the producer accuracy, the overall accuracy, and also to calculate something called a kappa coefficient, okay, which is nothing but observed accuracy minus chance agreement 1 minus chance agreement 2. You can read later and understand what is kappa coefficient, how it is calculated. So to find out, okay, now let us write one line. Let's go to our code where we calculated our random forest and cart outputs, and I am going to paste a line which says classifier dot confusion matrix dot accuracy. Okay, so what is this doing? It is, so once the classifier is run, it has got trained and on 8 points, and for 2 points I'm going to test it. But on the 8 points, originally what is the accuracy? You get my point? So you take 8 points, you train the model, maybe it saw that for 1 point is behaving abruptly, it has said I'll not consider the point, and it will train the model on the remaining 7 points. So generally the training accuracies are very high. So in this case it is saying the accuracy is 100%, it is 1. But what will be the answer when I say no, now you check based on the testing data. So if you classify for the testing data using the CART algorithm and find the error matrix, and then from the error matrix calculate the overall accuracy, kappa coefficient, user and producer accuracy and all that, when you run it, you will see that the overall testing overall accuracy is only 0.82%, whereas training accuracy, as I told you, is always higher, is 100% in this case. So this number doesn't mean anything in terms of classification, but this number is very important. So you need to maximize this number, try to maximize this number. This confusion matrix is also very nice. It says all the classes of 0 were predicted correctly, but class 1 out of 2 points, 1 got correctly predicted, but the other point went to some other class, and so on. In class 2, there were no points. In class 3, the 4 points were correctly predicted, but 1 point went to some other class. Okay, so and you get your kappa coefficient and all that. Okay, so this is how you calculate your testing accuracies on the test set, on the 2 points, on the 20% of the points that we had kept separately. We classify it after the classification is done, and then we create an error matrix. From this error matrix, confusion matrix, from this confusion matrix we generate accuracy, producers accuracy, consumer accuracy, and the kappa coefficient. So that is mostly what I want to tell about supervised and unsupervised classification using different machine learning techniques, and unsupervised using k-means, and a little bit about how to do accuracy assessment. A lot of more things can be done, uh, and obviously, if you have some access to Google Cloud, you can export this data to a Google Cloud storage and run deep learning algorithms. So currently, deep learning algorithms are not built in inside Earth Engine, but of course, you could create a Google Cloud project, export the data there, and probably run TensorFlow and all those deep learning algorithms also. Uh, the code that I used for this project is available on this link. So if you want, you can uh, use this link uh, to uh, to get all the code that I showed today. It is bit.ly/ 3 capital I, 5, then 2 small i's, and then LA, 3I5 IILA. You just type this in your browser here. It will take you to a Earth Engine Earth Engine code, which is basically everything that I showed today, including your clustered output and your accuracy assessment metrics. Okay, so we will stop here, and if you have any questions, I'd be happy to answer.